I'm going to be quick. Here today we have Dr. James Woodcock. He's a senior consultant as Arup. He is specializing in aviation noise and human response to sound and vibration. He did his PhD here at Salford with David, I think, on railway noise and vibration. At Arup is working on the assessment of noise and vibration for large infrastructure projects, and is having an expertise in acoustics, including design, implementation, analysis of perceptual tests, and developing realization methods, which I think is the main topic of today. And today you're going to talk about, or James is going to talk about the CAELUS project funded by Future Flight Challenge. So. Yeah.
Cool. Thanks a lot, Antonio. Cheers. So like I say, my name's James. I'm a consultant at Arup. And in this talk, I'm going to introduce some of the work we've been doing as part of the CAELUS project to gather data on how people respond to the sound of drones used specifically in the context of medical delivery. So the overall aim of the CAELUS project is to trial the UK's first medical distribution network using drones. And the primary objective of the project is to enhance kind of healthcare accessibility and equity between urban and remote rural communities in Scotland. So the project's big consortium project is funded by Innovate UK's Future Flight Challenge, and is currently being led by AGS Airports. Arup are doing the kind of noise side of things, but it's just quite a small part of a wider project that are looking at actually trialing this drone network. Though it's recognised that noise could be a significant barrier to the acceptance of drone networks, and that's been highlighted in kind of various studies and recent white papers by organisations like EASA and NASA. However, how people respond to the sound of drones, particularly in the context of medical delivery, is kind of currently unknown. So as part of the CAELUS project, Arup are developing an online listening experiment to gather data on people's response to the sound of drones used in this context. And obviously, we're going to make the results available to kind of industry regulators and in publications. We're hoping that they can kind of contribute to the evidence base of how people respond to drones, and can be useful in kind of future planning of drone networks and in the design of mitigation. So in this talk, I'm going to start by kind of going over the outcomes of a literature review and some industry engagement that we did at the start of the project to help shape the design of the study and the research questions. I'm then going to talk about how we developed and validated a method to oralise the drone sounds that have been used as the stimuli in the study. And I'll then talk about how we use these validated oralizations to design a listening test to measure how people respond to these sounds. The tests are live, but I've got some kind of preliminary results that I can present at the end of the talk. So to start with, I'm going to talk about a kind of literature review and the engagement we did at the start of the project. So this is a bit of background if people aren't familiar with how transportation noise is generally assessed. So the effects of transportation noise are generally assessed using exposure-response relationships. And these relationships generally describe the percentage of the population expected to express annoyance above a given threshold for different levels of noise exposure. So this figure on the right shows the kind of generally accepted relationships for aircraft, roads, and rail noise sources. And these are all based on kind of decades and decades of field research. Now we can see for each of the sources, you generally get an increase in annoyance, which is kind of what's shown on the y-axis, as we get an increase in noise level, as you would expect. However, we can see that the rate of growth in annoyance is different for each of the different noise sources. So you can see we get a much higher annoyance response for the same noise exposure for aircraft noise than we do for roads, than we do for rail. And this is due to differences kind of both in the acoustic characteristics of the sources, but perhaps more importantly, kind of attitudinal and contextual factors related to the source. So we generally find that people are, more accepting of railway noise than they are to aviation noise. Now, the issue we have with assessing noise from drones is that there's currently kind of no established relationships like this that we can use to assess their impact. So this makes it challenging for projects like CAELUS to design routes that minimize noise impacts, or to kind of assess how effective different mitigation measures around the takeoff and landing zones are. Now, there's a growing body of literature around how people respond to drones. I know a lot of it's coming out of Salford, which is fantastic. This slide just gives a kind of overview of some key papers if people are interested in reading some more. But some kind of general findings that come out of the literature are kind of, firstly, that drone sounds can elicit a higher annoyance response compared to other transportation noise sources. And this is often attributed to the kind of tonal characteristics of the sound. There've also been a few studies looking at the different kind of psychoacoustic metrics that contribute to annoyance. So it's been found that both kind of perceived noise level and sharpness contribute to perceived annoyance. So that's suggesting that there's also there's a level effect and also an effect of frequency that contribute to how people respond. And it's also been highlighted that further research is needed to better understand how people respond to drones kind of within existing soundscapes, and also how the ambient noise could affect, could mask drone operations. So alongside the literature review, we also undertook a kind of industry engagement exercise where we conducted semi-structured interviews with several stakeholders from industry, regulatory bodies and academia to help us better understand the concerns and issues related to operational drone noise. So I'm not going to go into too much detail, but the kind of main outcomes of that engagement were, firstly, there's generally a lack of existing evidence on the potential effects of drone noise on health and well-being. There's a need to capture response data on the kind of unique characteristics of the sound source. It was also highlighted that the kind of background sound and masking, the number of events and the time of day were expected to have a large effect on how people respond. And also that there are likely to be differences in attitudinal responses for different use cases. So we might expect people to respond differently to drone operations that have some sort of social benefit compared to kind of private or commercial use. So considering all of this, the kind of research that we're pursuing as part of CAELUS is aiming to investigate the public perception of the sound of drones, specifically in this context of medical delivery. The main research questions we're aiming to answer in the study are kind of firstly, how do operational characteristics such as the altitude and the distance of the drone affect how people respond? And we're also interested in how this relationship is affected by the existing sound environment. So do people respond differently if the drone's operating in a rural environment compared to an urban environment? Kind of linked to that, we're interested in how introducing the sound of the drone into the existing soundscape changes the perceived character of that soundscape. And finally, we're interested in whether the context of use influences the human response. So if people know that the drone has been used for medical delivery, do they respond differently than if they don't know how the drone's being used? And our proposed approach to this is basically to run an online listening experiment with sound demonstrations of drones operating at different altitudes and distances, and within different sound environments. And we are running the study kind of in two versions of the study in parallel, both with and without kind of contextual information on what the use of the drone is. And yeah, the expected outcomes of this are that we can kind of gather enough data to develop relationships that describe annoyance as a function of operational characteristics such as altitude and obviously noise level. But obviously, because we're running it online, there is some some difficulty in linking it back to absolute noise levels because it's not a purely calibrated listening experience. But we'll talk about that more in a few slides. OK, so I'm now going to go over how we develop the sound demonstrations that have been used as the stimuli in the study. So obviously, in order to develop the listening experiment, we needed a method to kind of flexibly recreate the sound of the drone operating at different altitudes and distances. And we needed to be able to mix that with different ambient background environments. So that we know that what we're presenting people is representative of what would be heard in a real-world environment. It's important that the oralizations are validated both objectively against measured field data and also subjectively through critical listening tests to make sure that the resulting oralizations are plausible. So the first step of this process was to go out and conduct a field survey, the aim of which was to collect audio recordings and acoustic data for a drone that's representative of the type that's going to be used in the CAELUS trials. I'm just going to skip forward a slide. So I've got a photograph of the drone that's going to be used. So this is what they're proposing to use. It's a kind of lift and cruise type drone. So we've got kind of 4 rotors on the top that operate when the drone takes off and lands. And then we've got these kind of two pusher rotors on the front when it's in cruise mode. And there's a kind of small hatch in the top that can take a payload for the medical delivery. I think it can carry about 5 kilograms. So yeah, so we had the opportunity to take measurements of the drone operating over a couple of days in the summer of 2022. We basically went out with an array of sound field ambisonic microphones, also high quality mono microphones, ground plate mics, and class 1 sound level meters. And this kit was positioned kind of in an array away from the flight path. And this allowed us to take kind of detailed recordings of firstly overflights at altitudes of 60 and 100 meters, and also takeoff, hover, and landing operations at altitudes of 40, 60, and 100 meters. Now we did have some challenges on site. So this was the only site where they had permission from the CAA to operate the drone. And unfortunately, it was close to both an existing airfield and also a recycling centre. So we were kind of competing with some quite high background noise. So I'm going to talk a bit more in a moment about how we dealt with that. But yeah, overall, we were able to measure, I think it's around 40 overflight events at those different altitudes, with the drone operating at a speed of 55 knots. As I said, there are high background levels on site. You can see the levels of the overflight events were relatively low when it's in its cruise mode. So we're getting L maxes of around 48 dB. Hopefully, if the audio works, I can just play one of the recordings from site, and you'll hear that the drone is quite quiet compared to the background. It's going to work. No.
Yeah.
So you can hear it actually sounds kind of like a small plane rather than the kind of quadcopter type drone that we're used to.
What altitude is that?
That's at 60-meter altitude. So that's typically what it sounds like during overflights. In terms of the kind of takeoff, hover, and landing operations, we again took detailed measurements using the same kits at distances of 10 meters and 60 meters from the takeoff and landing point. You can see we get much higher levels during these operations, so around 82 dB Lmax at 10 meters, around 66 dB at 60 meters. And I think this sounds kind of much more how you would expect a drone to sound. So yeah, this is a recording of one of the takeoff operations. Yeah. So yeah, you get the idea.
Sorry, James.
Yeah.
Those distances are lateral distances from the.
Yeah, that's right. That's right. So basically the drone, what we recorded was the drone taking off. It reached an altitude of, in the first instance, like 40 meters, hovered for 30 seconds or so, and then landed again. Yeah. Ooh, don't need to do that again. So yeah, so in terms of how we took that data to create the oralizations for the study, so kind of as I mentioned, due to the kind of relatively low noise levels of the overflight operations and the kind of high background noise levels on site, most of the recordings were kind of contaminated with background noise to an extent that we couldn't kind of extract the drone overflight from the background and use it directly in the study. So what we've done to overcome this is to kind of implement a method to kind of flexibly synthesize the overflight operations at any altitude, and then we'll have a clean signal that we can mix with the different background environments that we are interested in. So we've used a kind of modified version of the method developed by Hyuchi et al. At EMPA. So there's a reference there if people want to read about this method in more detail. But basically, the method involves kind of identifying the main sources of the drone overflight. So we use the ground plate microphones, microphone measurements on site to kind of identify the main components. So this figure on the right shows a spectrogram of a typical flyover. And you can see we've got kind of three main components there. So firstly, we've got this harmonic series, which is related to the blade passing frequency of the rotors. So that starts at somewhere around 200 hertz, and then we've got a series of harmonics. We also have this high frequency component, which we believe is related to the self noise from the motor. And then we have this kind of general kind of shaped noise component, which again, we believe that's related to the kind of airframe noise. So the way that the EMPA method works is that you basically create virtual microphone signals for your different noise sources. So in the case of the rotor and the motor noise, we've created kind of rotational speed dependent emission signals based on an analysis of those ground plate mics that we can use to estimate the speed of the rotor. I think where this method works really well is that you then introduce some statistical variation on that on the speed of the rotor that you're using to generate your signals. So you get quite a lot of realism and variation within your oralization. And then for the airframe noise, we just use kind of shaped pink noise. Then a directivity is applied to each of the sources. This all gets summed up, and then we have a kind of cascade of time varying propagation filters, so we can set a kind of target trajectory for the drone in terms of kind of XY coordinates over time, and we get kind of propagation effects related to geometric spreading, Doppler shift, atmospheric attenuation, and turbulence accounted for. And then finally, this is kind of converted to an ambisonic format that we can either play back in something like Arup Sound Lab, which are ambisonic listening facilities, or we can convert to binaural to play online. So as I mentioned earlier, it's important that we know that this method is resulting in something that's representative of what would be heard in the real world. So we've kind of validated the resulting oralizations against some of the data that we measured on site. So this shows an example of a power spectral density of one of the recorded overflight events. So that's shown by the blue line, and one of our synthesized events, which is shown by the orange line. And you can see that the methods, certainly in the frequency domain, is successfully capturing the characteristics of the drone sound. So we're picking out the blade passing frequency, the harmonic series, and the motor tone, and also we can see that the kind of broadband component is broadly the same shape as what we measured on site. We also went through several kind of critical listening sessions with expert listeners in Arup Sound Lab to confirm that the method resulted in plausible oralizations. So this kind of involved listening to the synthesized audio against what was measured on site, and it was all generally judged to be plausible. Now, in terms of the takeoff operations, so again, we looked at the ground plate mic data. So this figure on the right is a spectrogram of one of those typical maneuvers. So we have around 30 or 40 seconds of takeoff, then hover, and then landing. We can see that generally those operations are kind of dominated by these kind of unsteady harmonic components. Now, we did look at options of using the Kyuchi method to synthesize a takeoff operation. But when we went through that kind of critical listening process, they were judged as just sounding a little bit too synthetic. I mean, we were able to kind of capture these main frequency components, but just when you listen back, it just sounded very much like a synthesized signal. However, because we did have a decent signal to noise ratio on site for those takeoff operations, and we were able to use the kind of high quality mono recordings on site as the basis of the oralizations. So we basically took those mic recordings on site and then applied corrections for geometric spreading and atmospheric attenuation to kind of propagate those signals back to the listener position. So those are the kind of two methods that we're using to oralize the drone signals for the listening test. The kind of final step in the test is to combine the oralizations with the kind of 3 different ambient background environments that we're interested in looking at. So we've basically got a remote rural environment, a kind of small town village environment, and an urban environment. So these are all based on sound field recordings of actual environments. As these have been presented online, we've also created kind of visual representations of these 3 environments that can be presented alongside the oralizations. And obviously, as they're not being, quite often when we make these sorts of sound demonstrations, it'll be for like a public consultation, for example, where we're going to a specific area. So we create 3D videos of that area, but as this has been kind of distributed online to a wide sample of the population, we've gone for more kind of generic representations of the environments, which you can see here. So yeah, in total for the test, we've generated kind of 9 overflights and 9 takeoff demonstrations. So that's kind of three different altitudes and distances against 3 different background environments. So obviously I'm not going to play them all, but this is an example of one of the overflight oralizations. So this is within a rural environment at an altitude of 90 meters. Obviously, you don't get the spatial impression, but that's rendered out in binaural. So the intention is that people would be listening to that over headphones, so you get the kind of spatial impression as well. And then this is one of the takeoff operations. Okay, so that's how we've kind of created the stimuli. In terms of how we are kind of distributing that, obviously one of the challenges in deploying sound demonstrations online is that you can't control the absolute sound level presented to the listener. However, we're fairly confident, kind of based on internal research, that we can kind of use online sound demos to look at kind of differences between stimuli. So we believe that people can reliably, compare a set of stimuli against each other and look at differences in characteristics. We have designed this kind of setup phase to try to make sure people get as consistent an experience as possible. So prior to the demonstration, the listener is asked to go through this setup video where they're basically asked to reduce any sources of noise within their environment, and then to adjust the volume of their device so that until a recording of speech is at what sounds like a natural level, and then all of the drone demonstrations are kind of calibrated back to that speech level. And this is, again, something that we've successfully deployed on public consultations. How are we for time, Antonio?
We have 15 minutes, but I don't know we have.
I think, probably just need another 10 minutes. Okay, so that's how we've put the stimuli together, and kind of how we're planning to deploy the sound demonstrations online. So I'm now going to talk just briefly how we've kind of taken those demonstrations and used them to design a listening experiment to address the research questions that I set out at the start of the talk. So as I said in the introduction, the kind of aim of this whole piece of research is to investigate the human response to drone sounds used in the context of medical delivery. So we've designed a listening test to investigate this using kind of various established methods from perceptual testing and sensory evaluation. So if you're interested in learning more about that, I can recommend this book from Zakharov. But there's all sorts of papers and things out there on how to design a listening test. But the basis of the design is basically a full factorial experiment examining the main effects of two independent variables. So we're interested in altitude or distance, and also the effects of the ambient soundscape environment on response. So the test has been implemented on this online engagement platform called Commonplace. And we worked with them on the kind of user experience design and how we present the videos and the scales and so on. And because the sources are so different, we're basically running two separate experiments. So one for the overflight operations and one for the takeoff operations. And we've obviously gone through a process of kind of user testing of the experiment and a kind of pilot test with industry, and that kind of feedback has gone back into refining the overall experiment. So like I say, we're interested in investigating the following independent variables. So we have overflights at altitudes of 60, 90 and 120 meters. That was defined as the kind of operational range of that type of drone. We've then got kind of varying distances from the takeoff point, so 30 meters, 60 meters and 120 meters. And then we've got our three different ambient background environments, so whether it's rural, village or urban. So see, we're doing these two parts separately, so that means whichever test the listener is doing, they're required to rate 9 stimuli. So in terms of response variables, so we're asking kind of three response questions. So first of all, we're kind of interested in how audible the sound of the drone is within that existing ambient environment. Something we were really interested in was looking at how introducing the sound of the drone affects the overall perception of the soundscape. Now, obviously, to do a full soundscape assessment, you would have to ask many different questions, and we felt that was probably too much for an online experiment. So what we tried to do is just to get at how how people feel the perceived soundscape has changed. We're just asking how much the sound of the drone has changed the character of the existing soundscape. And finally, probably the thing we're most interested in is the annoyance response. So we have a question that's based on the wording of ISO 15666. So basically asking to what extent you're personally bothered, annoyed or disturbed by the sound of the drone. And this is the interface that people see. So you have the video of that specific stimuli, you hit play, and then you've got responses to those 3 questions on a 7-point scale. And then we are collecting some additional kind of qualitative information at the end of the study. So we're asking people if there are kind of any particular characteristics of the drone sound that kind of determine their response. We're also asking people if they believe the purpose or the application of the drone would have affected their response. We're also interested in what type of area people currently live in. So whether they do actually live in a rural environment or an urban environment. And finally, just any kind of general comments or feedback. And then, yeah, the final thing we're interested in looking at in this study is the influence of context. So whether people knowing that the drone is being used for medical delivery is going to affect their response. We believe it probably will do. So to investigate this, we're kind of running 2 parallel versions of the survey. So we have one version which is on the main CAELUS website, where the listener kind of lands on this landing page. They've got all sorts of contextual information about how the drone is going to be used. It's like an FAQ section. And then the second version of the study is just a kind of generic landing page where it's just a drone noise survey. So they're not given any additional information on what is the use of the drone. Other than that, the studies are identical. So what we're hoping to be able to do is to essentially use that which study the participants completed as a variable in the analysis, and then we'll be able to do kind of ANOVA type statistical analysis to look at firstly whether there's a significant effect of that variable, and if there is, quantify what the magnitude of that effect is. So like I said, the study's still live, so we've not had a chance to look at the data in detail, but this is just kind of some preliminary results that are coming out. So this is just showing the annoyance response for the overflight events at different altitudes. We've got the kind of outcome of an analysis of variance. I don't know how familiar people are with this, but basically what you need to look at here is the p-value, and whether if that's less than 0.05, then generally you can say you've got a significant effect of that variable on your outcome. So you can see, with both the altitude and the type of soundscape are significantly contributing to the annoyance response. And it also looks like we have an interaction effect. So that would suggest that the kind of rate of growth of annoyance is different for the different soundscapes. But yeah, you can see from the bar plot, I mean, actually the altitude is it looks like a relatively small effect compared to the soundscape. So that's quite interesting. And I think that makes sense considering if you look at the actual overall level difference between 60 and 120 meter altitude, it's relatively small. It's maybe 5 dB or something. And then, yeah, in terms of the takeoff events, yeah, obviously, as expected, we're getting a much higher annoyance than the overflights. But again, it looks like we've got a significant main effect of both the distance from the takeoff points and also the type of soundscape, and again an interaction effect. But yeah, obviously there's going to be a lot more analysis to do, but generally the preliminary results look kind of the direction of the relationships is as we would expect, and it's looking like we've got some statistically significant results. So yeah, kind of watch this space, and hopefully we'll have an interesting publication going over all of the findings. So just in summary, we believe that noise is potentially a key barrier to the public acceptance of drone operations. But there is currently a limited evidence base that we can use to assess the impact of noise from these sources. So to address this, Project CAELUS have launched an online listening experiment to gather data on how people respond to the sound of drones, particularly from in a medical delivery context. And yeah, to deliver this, we've developed a flexible oralization method, which has been validated objectively and subjectively against field measurements. And then, yeah, a listening test has been designed based on these oralizations. So yeah. Well, I mean, thanks a lot for your time. There's some contact details on this slide if you wanted to get in touch and find out more about the study. So you can contact me and Adam Thomas at Arup. If you're interested more generally about the CAELUS project and what they're getting up to, there's a project website and a LinkedIn page, and also a project email address. But yeah, I think that's about it for me. So thanks a lot, and I'd be happy to answer any questions.
Thank you, James. There's one question online from Bruno. So Bruno, question. So is the B format synthesized in higher order ambisonics? If so, which order? And another question is, presume that listening was not heat tracked, were listeners looking straight ahead, up, etc.
Yeah, so I'm just trying to think back. So definitely the ambient soundscape environments of first order ambisonic recordings. Mm-hmm. I believe that we rendered out the drone overflights as third order ambisonics, and then they were obviously all kind of rendered back out as binaural. So obviously doing convolution with HRTFs. Mm-hmm. And to answer the second question, no, it's not head tracked because it's just obviously we're distributing it online with static videos, but yeah, I mean, we could in theory do head tracked audio if we put it into VR, but yeah, in this instance it's all static.
Yeah. Anyone here in the room? Mike?
Yeah, thanks, James. Cheers. I just had one question about the visualization.
Yeah, sure.
I just wondered what the thoughts were, what your thinking was behind the way that the visualizations were done as a sort of isometric model, as opposed to using, video recordings or something like that could have been used, and how much of an influence you think that could have. Do you have any plans to investigate that, that kind of thing?
Yeah, I mean, that's interesting. I mean, like I say, we kind of gone down that kind of isometric route to keep things quite generic, so it wasn't specifically in someone's area.
Yeah.
I mean, they were partly intended as almost to aid the spatial sense, so it was kind of a pointer as to where the aircraft was in the sky at that moment. But yeah, I think kind of trade-off, as you say, from having like a ambient video is that you've probably got a bit less immersion. So yeah, I don't know what effect that would actually have on the outcomes, but it would definitely be something that'd be interesting to look at. Is
this project pretty much like complete, and in terms of obviously you're doing the analysis, but I mean in terms of surveys and so on, data gathering? Yeah,
that's right. We're just finishing up I think the online experiment's going to be up for another couple of weeks, and then we've got a couple of months of analysis. But yeah, it's all going to be wrapped up this financial year anyway.
Right. Thank you.
Any other questions? Josh?
Thank you. Is there any intention to look at how annoyance changes with like the age of your participants? Maybe older people are maybe more annoyed, or
yeah, just in general. Yeah, I mean that would definitely be something that would be interesting to look at. So this commonplace platform collects all sorts of demographic information.
Yeah,
so you don't have to provide that information, but I think most people have been. So we do have that as a database. We also have information on how people's familiarity with drones, like ranging from like I've never heard of a drone to like I work in the drone industry. So we also think like that familiarity with technology could also have an effect. So yeah, we've got all sorts of data. It's just
a few
hopefully we've got time to
processing.
to process it. Yeah.
The two kind of cases you're dealing with, the sort of fly past and the takeoff, obviously had very different levels, but they also have very different character of sound. So here's an impossible question for you. One of them sounds quite natural. So the aircraft manoeuvring when it's taking off has that angry bee sort of characteristic to it, whereas the distant is more like either a drone or a buzzsaw going on in the distance. So how much do you think the connection to possibly a real sound like bees attacking you influences how you will respond to that particular sound? And if we could make drones not sound like angry bees but sound like friendly bees, would it make them less annoying?
It's a very, very good question.
I mean, how does your data prove all that? That's right.
Yeah, I mean, I think that you probably know about this, Antonio. I think people have looked at perceived threats, haven't they? So that maybe ties into it. So how threatening you feel the sound is. But
yeah, I think one of the reasons why that's happening in this, I don't think there's anything wrong with the way the sounds were generated, is because there are two different sources.
It's so different, isn't it? Yeah.
4 rotors spinning quite fast, while this flying overfly is basically 2 small propellers at the front. So the act is like 2 drones at the same time.
We were quite surprised when we got on site hearing the different.
But it's really interesting because it's quite complex to get that to get right that the realization of that, that character of the drone is really difficult to get that. So when I was looking at your diagrams, the overfly, you get it really well, and it's quite a lot of consistency between the recordings and the realization. The problem is when you want to, as you said, when you want to auralize that takeoff landing, which is more big.
It's kind of chaotic, isn't it? Because you've got the interaction between the rotors, and it's
it's quite challenging. I think anyway.
Thanks. Very interesting. I wonder if have you used some information about buildings or acoustic shadings or diffraction in the urban environment in order maybe it's going to be reduce the annoyance, which is not very prominent in rural ambience. So you have more plain terrain.
Yeah, I think that is going to have an influence, definitely. So all of our realizations are just flat ground models, so we're not taking into account any shielding of buildings or reflections within the environment. But that would definitely be something that would be interesting to look at, because I guess that could contribute to how you might decide to site a takeoff and landing zone, if you can take advantage of a kind of existing screening and so on. But it's not something that we've looked at in this study.
And I have another question. Related with the blade passing frequency you include for the realization, did you consider just only one value, or because I assume there are rotating four motors at a time, so maybe you have considered slightly difference between each?
Yeah, so I think that's one of the nice things about this MPER method is you kind of include a statistical variation of the blade passing frequency within the model, and it gives it that kind of natural variation. So we essentially use the field data to kind of isolate the first harmonic of that source, and then did a kind of back calculation to work out what the blade passing frequency would be over, sorry, what the rotor speed would be over time. And then we use that to characterize a kind of statistical variation of the rotor speed and brought that into our model. So you've got the two separate motors, you've got them varying at slightly different speeds, and that's what starts to give you that kind of slightly detuned sort of character to the sound. Yeah, it seems to work quite well in terms of the plausibility.
Thanks.
I think it's Rebecca first and then Mark.
So sorry, I know virtually nothing about drones, so forgive me for asking a stupid question. I'm assuming the aim of this research is to make drones less annoying. So how is that being done?
Yeah, I mean that's a good question. It's whether it's making.
I mean, it's all very well like knowing that they're annoying, but like how are you making them less annoying?
I mean, it's whether it's a good question. I mean, you can obviously you can use this sort of outcome to look at what specific features of the sound are contributing to annoyance, and then perhaps use that in the design of the rotors of the drones. But I think it is probably more about, as well as making them less annoying, just having some a set of like a base, an evidence base that you can use to assess what the actual impacts would be. So it might be that when you're trying to design routes for the drones, for example, knowing at what level that annoyance starts to kick in, then you can kind of try to design your routes so they're going away from populated areas, this sort of thing.
And
So my question, I guess, is kind of semi-related to that and semi-related to what Trevor was talking about. You mentioned that in some of the backgrounds there are presence of other aircraft sounds. I was wondering if that's something that you have or can specifically look at, and also does the affective response of the participants change as the sound of the drone approaches the sound of a conventional aircraft? Because there does seem to be this kind of crossover where it's maybe for the takeoff it sounds very definitely like this is a drone, but for the overflight it's like, it could be some kind of conventional aircraft. I kind of know what this is, and how that.
Yeah, that's a good point. I mean, I don't think we've got a way of looking at in the data that we've collected, but yeah, maybe something around familiarity with the source could be really interesting. Yeah, I mean, it could be something that we've not looked at the kind of qualitative data yet, and what where we've asked people what specific features of the sound contributed to their response. So it could be that we have something in there on that, but no, we didn't look specifically at conventional aircraft.
Fair enough. Yeah, no, it's just interesting. We're thinking about doing some kind of machine learning thing with audio from conventional aircraft recordings and whether that actually transfers. So it's just kind of something that.
Can I make a suggestion? You know about live briefs. Perhaps Antonio could offer a live brief that would allow you to analyse some of those data under your supervision. It's just a suggestion, a live brief looking at some of those data. Yeah, it doesn't matter if it doesn't work. You know what it's like with these MSc projects. Sometimes it does, but then again, sometimes you can come up with something quite surprising. Some of these master students.
That's a good suggestion.
And probably final question from Woodcock.
My question is about the online listening test. So anyone can access this test from the website, right?
Yeah, that's right. So
and they have to use their own headphones.
Yeah.
Yeah. So is there any way to ensure that? Are you taking any measure to ensure that they are actually putting on the headphones rather than listening to?
Yeah, I mean that's a good point. I mean, I think the best that we can do is to have this kind of like I say, we've got this setup video at the start where we we say to people, get your best quality pair of headphones, try to reduce the sound in your environment, but I don't think we've got any way of feeding back what they actually used. I mean, it's an issue with online listening experiments and online engagement in general, I think. But I suppose the advantage is you're getting a bigger sample. You're going to get obviously much noisier data than you would in a lab, but you can get data from hundreds of participants rather than 50 participants.
And since they are all using different headphones. Do you think is there any way to account for that issue? Like, I don't know, maybe taking the name of their headphones or the label?
Yeah, I mean that could be. Yeah, you could potentially, if people could provide that information for you, and you had some knowledge of what the response of the headphones is, you could try to take that into account. But yeah, it's definitely one of the challenges with online listening experiments, and I think it's where, you know, we're like I said at the start, I think we're quite confident that we can look at relative differences between stimuli, but obviously we can't really say anything about the absolute level, because, you know, people could have quite different presentation levels depending on how they've interpreted that calibration step.
There is actually a process signals you can send to them to see if they're wearing headphones or not.
Yeah.
Around with left and right signals. I can't remember who invented it. There is a way you can.
Oh, okay, that's interesting.
Basically, tell you if they're wearing headphones or not.
So you hear a certain sound if they are putting on the headphones, right?
There's loudspeakers. I can't remember exactly how it works.
I forgot its name as well.
I did an online experiment once, and you have to pass a test before actually doing the.
Oh, really?
Yeah,
That's
interesting. It was like 3 or 4 questions, like just to check whether you're in a quiet environment.
Yeah.
Probably whether you're having headphones or these sort of things.
That's interesting.
So I suppose you can integrate something like that into an online listening test, right?
Nathan is asking about how many.
Nathan, just very quickly, that would be very interesting if they failed the 3 tests and you still collected the data and analysed those data. That could
Yeah.
Sorry to interrupt.
No, it's, Nathan is asking how many participants in the online experiment, if you know more or less how many.
Yeah, so I think we've.
About 600.
Yeah, well, so we've got a really good response to the. So this was the one without any context. So we've got kind of in the hundreds. In that case, like I say, there's still data coming in. We're still trying to get more participants for the version where they know the context of the study. So we're looking at options to increase that, because I think we've got somewhere around 100 for those at the moment. But yeah, we're hoping to try and get at least 100 participants in through each of the experiments.
Could you go to slide 32, because this is connected to what Becky said before, and what you said about kind of optimizing flight paths. I think these results are quite consistent with Andy Christian, that paper from 2017, when they did they presented the sounds at different altitudes, and they didn't find any significant difference in the altitude. And I think it's because the noise of the drone is too intrusive, that from the moment you detect it, you know, the altitude of the distance is second order effect. So I think that's one of the issues when you are trying to optimize trajectories.
As soon as it's
from the moment it's audible, is detectable, is going to be challenging to reduce annoyance.
Yeah, I think it'll be interesting looking at we collected data about audibility. So looking at, you know, if we can start to see at what point it becomes audible.
If I may point you to Eulalia's work at this point, the higher it is, the smaller it's going to be. So the size is a little bit smaller, so you can't see it as well. You know, we found with trains whether you could see it or not was important, and even what colour the train was was important. So whilst just the sound and the percentage highly annoyed might not change, the overall annoyance and acceptance, which is what we're interested in, might vary with altitude.
Yeah, good point.
Okay, any other question before we finish? Not. Okay, thank you, James, again.
Cool, thanks a lot.